So I was saying, my name is Ben Difrancesco. I run a small software consultancy based out of Philadelphia called Scopelift. These are some places where you can find me on the internet, and please, by all means, do reach out. I love to meet and talk to my fellow developers. Please come up and chat with me during the rest of the conference. I'd love to talk and compare notes. Just a little warning, I did lose my voice over the weekend, and it's back now, but it's not like 100%. So I apologize in advance if I need to grab some water during the talk, and hopefully this won't turn into an interpretive dance at some point, but we'll see how it goes. So, the title of today's talk is Threads, Queues, and Things to Come, the Present and Future of Concurrency in Swift. So as the title suggests, there are going to be kind of two sections to the talk today. In the first section of the talk, we're going to talk about concurrency in Swift today. So we're going to talk about Grand Central Dispatch, GCD, and NSOperation. So these are tools that we have available to us in Swift on Apple's platforms today for writing concurrent code. But of course, both of these are libraries that bridge into Swift. So the second part of the talk is going to be looking at what writing concurrent code might look like in Swift in the future. And in particular, we know that at some point, Swift is going to get a native concurrency model. This has been discussed somewhat on the Swift evolution mailing list. And we're also going to take a look at some examples from other languages to imagine what a native concurrency model in Swift might look like. But before we jump into those topics, I want to take just a second and address the question of why do we want to write concurrent code in the first place? What is the benefit that we're seeking? What are we getting out of writing concurrent code? And this is a fair question to ask because writing concurrent code can be a little bit mind-blowing, right? It's not linear. We're not executing code down the page, down the line of text as we're used to. And so if we're going to take on this additional kind of cognitive load and write our code concurrently, we better have an understanding of what we're seeking to gain from it. So in 2017, there's actually a pretty straightforward answer to this question, and it's cores. So all of our devices today are pretty much multi-core, even our watches. These tiny little computers that we wear on our wrists now come with dual-core processors. Our iPhones are quad-core, so they have 4 cores. Our MacBook Pros, these things have 4 cores, but they're Intel processors. And Intel does this thing called hyperthreading. So they duplicate some of the hardware in the processor, specifically some of the registers. And then they do these really cool low-level software tricks where they're actually kind of threading instructions in between other instructions during clock cycles, in between clock cycles. So essentially you get 8 parallel threads of execution on 4 physical cores. So for all intents and purposes, you have 8 cores available to you on a laptop these days. And then you get to talking about desktop computers, like this bad boy announced at WWDC, the iMac Pro, supposedly coming sometime in December. And this uses, in its top-of-the-line configuration, Intel's chips that have 18 cores. So thanks to the aforementioned hyperthreading, that's 36 threads of parallel execution. So when this thing is humming on all cylinders, it looks something like this. And if your application is still single-threaded, then your application looks something like this. So that's a lot of sad, unused cores sitting around doing nothing. And if your competitor's application is leveraging this ability for parallel processing, it can be 36 times more performant and more responsive to your users than your application will be. So cores are definitely one reason to write concurrent code in 2017. But even before we talk about multiple core processors, there's actually a lot of benefits that you can get from concurrency. So this is the original iPhone. It had a pretty bad 412 megahertz single-core ARM11 processor. But if you talk to people who had one of these phones, did anyone have one? Anyone have an original iPhone? So I didn't. I had a different cell phone. I had a Palm Pre with WebOS, and unlike that phone, the iPhone, the original iPhone, was always responsive to user touches. So people that had it will tell you it may have taken forever to load a website or to render an image, but even while it was doing those tasks, you could always pan around, you could pinch to zoom, you could tap buttons and return to different places in the interface. So it always responded to user touches, and that's because of the way that Apple leverages concurrency in iOS. So we're probably used to, as iOS developers, anytime we touch something in UIKit, we have to do it on the main queue. We have to dispatch to the main thread. And that's because when you have multiple threads of execution, even if only one of them can actually be running on the physical core at a time, the operating system can prioritize some work over other work. And Apple has very carefully tuned iOS to make sure that UI work on the main thread always takes priority over anything else that you might be doing. So if you code your applications in the right way, your UI will always be responsive. So there are benefits to concurrency even before you talk about parallelism. Parallelism specifically being running code at the same moment in time on multiple cores. So this really, I think, shows the primary reason why we should be focused on concurrency in the first place, and that's providing better user experiences. Especially as iOS developers, our goal when we reach for concurrency should be to provide a better experience to our users, and that should be at the forefront of our mind. So, with that in mind, let's go ahead and jump into talking about how we can do that today on iOS and Apple's other platforms with the tools that are available to us. So the first of those that we'll talk about is Grand Central Dispatch, or GCD. And you could think of the primary abstraction that GCD gives you of a dispatch queue. You can think of that as basically being a level of abstraction above an operating system thread. So there are libraries in Cocoa that you can access and work with traditional operating system threads and locks and all those kinds of low-level threading tools. But today, you really don't need to go below GCD. And what a dispatch queue gives you is basically a pipeline of work that has some characteristics you can configure, and then you put work into that pipeline and the system will schedule that work to be done on actual operating system threads. So what are some of those properties that you can configure on your dispatch queues? The first that I'll mention is the quality of service, or the QoS, and this is basically a ranking of how important this work is, and specifically how important this work is to your users. So I love this about this API that Apple gave us. They specifically put in the forefront thinking about how important this work is for the sake of your users. So there's 4 levels: user interactive, user initiated, utility, and background. User interactive basically means that the UI will literally block. It will be unusable until this work gets completed. User initiated is kind of a step below that. It's something that the user initiated, they started, and they might be waiting for something, but the UI is not going to lock up. And then utility and background finally being the lowest levels, basically unimportant to the user directly. So another property that's important on a GCD queue is whether it's serial or concurrent. So every queue will be one of these two. A serial queue is first in, first out, and it processes one task at a time, and each task has to complete before the next task has an opportunity to run. Now on the other hand, a concurrent queue guarantees that it will start the tasks that you give it in the order that you provide them to the queue, but they'll finish arbitrarily. You can't count on them finishing in order at all. And in fact, if the system has resources available, it may run those tasks in parallel. So let's look at some examples of using Grand Central Dispatch queues in real situations, with remembering that we're keeping our user experience in mind. That should be at the top of our mind. So the first example here is using a serial background queue in the context of doing some system logging. So we're going to create a logger class, and internally we're going to instantiate a serial queue just by creating a dispatch queue and providing a label and a quality of service. And we're going to choose a background QoS, because while our logging may be important to us as developers, it's not important to our users, and we don't want to prioritize the work of logging over anything else that the application may be doing. So we don't have to tell the queue that it's serial when we instantiate it. That's the default. And then we're going to use this queue inside of a log function that we're going to expose on our class. So it's going to take in a message, and then it's going to dispatch asynchronously on our serial queue. And in that block, we would do the work of actually writing the message out to the log file. Now, one thing to notice here is that we've chosen to dispatch asynchronously on our serial write queue. And it's easy to get those two concepts confused. At least that's something that I had trouble with. But they're really orthogonal to each other. Whether you dispatch asynchronously or synchronously doesn't impact whether it's a serial queue or a concurrent queue. And in this case, we've actually chosen asynchronously because we want this log message to return immediately. So we want this method to return. We don't want the user waiting around, even if it's for just a few milliseconds, for our disk I/O to actually take place. So we'll do that somewhere in the background. The other thing to note here is why we've chosen a serial queue in the first place. So we're writing out to a log file. This is a shared mutable resource. And if multiple threads try to write to this file at the same time, say you're doing some logging from a network callback and also on the main thread for some UI, if multiple threads tried to write to this file, then at best you're going to get garbled data. At worst, you're going to get a completely corrupt file or maybe even a crash. And so anytime you have a shared mutable resource, you need to protect that resource from being manipulated by multiple threads concurrently. And so a serial queue is a great way to do that. Let's look at another example here. This is a concurrent user-initiated queue. In this case, we're imagining a scenario where we're applying some filter to an image. And we're going to imagine that that render filter function that we're calling right in the middle is a pretty expensive call. It's something that's going to take some time. So we don't want to lock up our UI. We would never do this on the main thread. So we're going to dispatch on one of these global queues with a quality of service of user-initiated. And we'll dispatch asynchronously. Now these global queues are a pool of queues that are created when your app starts up. They're always concurrent queues. And they're available to you when you need to do work in the background. And a lot of times, if you need a concurrent queue, reaching for a global queue is the right way to go. You save the overhead of creating the queue yourself. Now once we have our filtered image, we need to set it back to some image view or maybe a collection view. And so we're going to do that by dispatching asynchronously on our main thread. And we talked about earlier why Apple imposes that limitation in iOS. So GCD has a ton of other features. That's really only scratching the surface. You could do a whole talk on some of those other features. I want to just touch briefly on one of these more advanced features, specifically dispatch groups. And we're going to see this come up in some sample code later in the talk. So dispatch groups are interesting. They let you do a couple of things. You can instantiate a dispatch group, and then once you have it, you can enter the group, you can leave the group, and you can tell the group to wait. And when you enter the group, you can think of that as incrementing an internal counter. And when you decrement a group, you can think of that as decrementing the internal counter. That's leaving the group, sorry. And then when you tell the group to wait, what you're saying is, I want to block the current thread until that counter gets to 0. So hopefully this isn't the main thread, but some background thread. And this is useful in scenarios, for example, of when you might have multiple network requests. So those are going to be asynchronous requests, but you might have to coalesce the data, all of the data from those multiple requests before you show something to the user. So you can enter a dispatch group before each request and leave it in the callback. And then you can tell that thread, hopefully again a background thread, to wait, and you know that you will have all the data available to you when the line of code after group.wait executes. So we'll see how this works later in some samples. So let's move on and talk about NSOperation_queue. So if GCD is a level above an operating system thread, I would say an operation queue is a level above GCD. These are real objects, specifically they're Objective-C classes, and to provide work to a queue, you subclass NSOperation and override the main method. So these sets of classes are really powerful in the kind of dependency hierarchies of work that they allow you to express. So let's see how they do that. So there are some properties on an operation queue that you can set. The first that I'll mention is the max concurrent operation count. So this is how many operation instances will be allowed to run at once. So this can be useful in a lot of scenarios, but in general you may have a lot of work that you need to do. You may have 100 tasks that you need to execute. Now we know that our phones have an increasing number of cores, but they don't yet actually have 100 cores. And so if you were to actually fire off in parallel 100 different jobs that all needed to get onto the CPU, you might actually create some resource contention, and that would actually result in worse performance than if you throttled it. So max concurrent operation count gives you a very easy way to throttle the number of jobs that will ever run at the same time. Another useful property is the isSuspended property. So this is a Boolean property, and if you set this to true, it will pause the operation queue. It won't allow the next operation to start. and it will save the state of the operation queue until you toggle it back to false, and then it will resume. So this is good if the user, say, changes contexts, and you need to free up resources for whatever they've asked the app to do, but you want to remember the work that you were trying to do in the background and resume it at some later point in time. So NSOperation, or just operation in Swift, is again the unit of work that you provide it to the operation queue. And to do that, you subclass operation and override the main method. And you just, in the main method, serially execute the work that you need done for this operation. So operations are configurable themselves. They have a QoS, that's that same quality of service property that we saw in GCD. Operations are also cancelable, which is useful. So you can cherry pick one piece of work out of the queue if, say, the user cancels something and you want to free those resources up. Operations can also have dependencies, and this is really, really powerful. So say you have one piece of work that you need to do, but in order for it to complete, it needs some data that's going to be generated by another operation. So you can simply set one operation as a dependency of another. You can dump both of them in the queue, and the operation is going to take care of making sure that the dependent one runs only when the other is completed. And a single operation can have multiple dependencies. These can be nested as well, so you can create these hierarchies of tasks that need to be completed, dump them all into the operation queue, and let the queue figure out how to run them in the most efficient way. So to demonstrate some of the power that we have in these two tools, I want to show some sample code. We're going to build a simple client for everyone's favorite toxic programming community, Hacker News. So if you're not familiar with Hacker News, you're probably more productive than those of us who are. You can kind of think of it like McDonald's, but for the programmer's soul. You know, like consuming it is killing you little by little, but it's really good. So, all right, let's move on. What is our client actually going to do? Well, Hacker News has actually a pretty nice API. It's an open API. You don't need any credentials to start playing with it. And it has an endpoint that you hit to fetch the top 500 stories currently on Hacker News. But it doesn't provide you the list with all the story data included. Instead, it provides you a list of unique identifiers for those 500 stories. And then there's another endpoint that you have to hit to fetch the story data for that specific story. Now, a very naive implementation would just be to go and to fetch all 500 stories and show your user a spinner until all of those requests completed. But obviously 500 network requests is going to take a long time, and that would be a terrible user experience. So we want to start loading this data, and as soon as one story is available, we want to make that visible to our user, and we want this cell to be tappable and actionable. And we can run a number of these at a time, and as they run in parallel, we're going to show more data to our users. We also want to fetch an icon to show alongside the story, but this icon isn't something that's provided by Hacker News. We're going to fetch the fave icon from the website where the story is hosted. So the fave icon is like the little icon that shows in the tab of your browser if you're looking on a normal web context. So we want to load in that fave icon and display it, but in order to get the path to the fave icon, we have to know the URL of the story itself. So that's a dependency of the first fetch operation that we have to complete. So we'll start loading those icons in as soon as they're available. And of course, over time, all of this data is going to become available to our users. So this is what we're going to try to create. Now, I'm going to show some code. There's a lot of code here. I don't expect you to follow everything that I'm doing. It is going to be available on GitHub afterwards if you want to take a look. But what I want to drive home is that it's fairly straightforward to put together the semantics that we're looking for and to execute the code in this way and provide a better user experience. So here's our table view controller. I want to point out a couple of things here. First of all, our table view controller has this stories fetcher object, and it's using a stories property. This is a list of Hacker News stories on that fetcher object to populate the table view. So the details here aren't really that relevant. It's pretty standard, but it's just using this fetcher object to grab the data and configure our cells. Now in our viewDidLoad method, we're going to call this reload stories, and this is just a helper function. And inside reload stories, we're going to call an API wrapper. This is a simple API wrapper just using NSURL session to hit that Hacker News API. And we're going to fetch that top list of stories. And remember, this is a list of unique identifiers, just the IDs, not the stories themselves. So if that's successful, we're going to take those stories and we're going to use them to instantiate our stories fetcher object. We're also going to provide an update callback to this fetcher. And this callback is going to get run by the fetcher object every time it has new data available. And so whenever the stories fetcher tells us that it has new data, we're just going to reload our table view and make that data available to our users. So once we've instantiated this object, we'll just tell our fetcher to start loading. So inside our story fetcher object, as you might have guessed, we've used an OperationQueue. And that OperationQueue we're just going to configure with a max concurrent operation count of 4. Now you'll note that we're not actually doing processor intensive work here. What we're doing is multiple network requests. Those too can be run in parallel, so the network controllers on our modern phones can duplex requests out and do things in parallel, so we want to leverage that. I'm just taking an educated guess, with 4 being a good number for performance. You might want to actually test this out lower and higher and see where the sweet spot is, but it's a reasonable guess. I'm also going to create a serial dispatch queue here, and we'll see what that's used for. Now if you remember, when we instantiated this, we provided a list of story IDs, so these are those unique identifiers. This is just a type alias for integer, by the way. And then we provided our callback. This is the onUpdate callback. So we're going to save that callback. It's an escaping closure. And we're going to run it, we're going to run it anytime our list of stories that we're exposing is updated. Now, in our start method, we're going to iterate over each of these story IDs, and we're going to do a couple of things. We're going to create a story fetch operation and an icon fetch operation, and we're going to add both of those into our fetch queue. Now, both of these operations have a completion block, and this is a completion block that this comes on NSOperation, so it's a property on NSOperation, and the OperationQueue will call this block exactly once when the operation completes. And what we're going to do when that happens is we're going to grab the story that was fetched, if it was successful, and then we're going to take that story and insert it into our list of stories. And you'll note that when we're doing this, we're doing it on a serial queue. That serial Grand Central Dispatch queue that we created earlier. Now that's because our list of stories is a shared mutable resource. It's an array in memory, but mutating an array is not an atomic operation in Swift. So in order to prevent, in this case, dropping values is actually what you could see happen, you have to ensure that only one thread, only one operation as it completes is ever going to access this at a time. And so we do that, again, with a serial queue. Now our icon fetch operation is very, very similar. It has a completion block, it grabs the icon that was fetched, it updates the story in our list to include that icon. The one thing that you'll note that's different is that we add a dependency to our icon fetch operation. And that dependency is just the story fetch operation that we created earlier. We just dump both into the queue, and again, the queue is going to work out starting the icon fetch operation only after the story fetch has completed. So now let's look at what these operations themselves actually look like. They're subclasses again. They expose a property for the story once it's been loaded. We instantiated our story fetch operation with the story ID. We're going to set our quality of service to user initiated here. And then our main method that we're overriding, this is where we do the actual work of the operation. So this is what the queue is going to call when it's our turn to execute. So we're again using an API wrapper to fetch the story with the story ID. If that's successful, we just hang on to that story so that up earlier we can extract it in our completion block. Now there's one thing that you'll notice that I'm doing here that might seem a little curious. I'm using a dispatch group. I'm entering that dispatch group before my network request. I'm leaving it in the callback. And then I'm telling my main method not to return. I'm blocking the thread until that counter gets to 0, until that group.leave call is executed in the callback. So this is an asynchronous request. It's using NSURL session under the hood, so it has to be asynchronous. But we don't want this operation to complete until we know that we've got that story data. So I actually have to serialize this request inside my main method itself, and an easy way to do that is with a dispatch group. So our icon fetch operation is very similar. Again, we override the main method, I'm making an API call, I'm using a dispatch group to serialize it. The one thing that I'll point out that's different here is that the first thing the icon fetch operation does is reach into its list of dependencies, grab that first dependency, which we know is a story fetch operation, in this case it's the only dependency, and it pulls off the story that it knows must have loaded by the time it gets the opportunity to run. And we have to do that because, again, we need the data from that story to derive the URL for the fave icon that we're actually loading. So I know that was a lot, and it was kind of a whirlwind through this code. I know you may not have followed every line that I showed you, but I hope you see that with only about 150 lines of code, we were able to express these semantics that we wanted. So let's go ahead and try to run this in the simulator. Actually, in this case, the slow hotel Wi-Fi may be an advantage, because we're going to be able to see this kind of playing out as our stories load in. Yeah, so nice and slow. But you see, you also note something. I have very chatty log output back here as all these stories are loading, and if we scroll fast enough, we could find the threshold. I won't bother with that. But if I click on one of these, you'll notice that my log output stops, and it loads the story up. And then once Safari View Controller is done, if it ever finishes, hopefully you'll see that logging output from my operations resume. There it goes. And what I've done here is I've used that suspended property on my queue, and I've said if the user taps a story, I want to pause my queue because I want all the bandwidth that's available, in this case not very much, to go toward loading the user's story in Safari. But once that is done, I can resume fetching the rest of the 500 stories that are down in the list. So again, these are very powerful classes that allow us to very quickly optimize things in a way that are going to produce the best experiences in our apps. All right, enough of that. So, hopefully I've convinced you that concurrency is very useful and that we have powerful tools available to us right now in Swift that make it not as intimidating as maybe you originally thought that it was. And while we do have powerful tools available to us today, we know that down the road we may have even more tools, especially in Swift, because we know that there is going to be eventually a native concurrency model coming to Swift. We know this because people on the Swift core team have said as much on the Swift Evolution mailing list, but actually beyond that we don't know a ton. In terms of timelines, obviously Swift 4 is basically already here, so the earliest we could expect to see it is in Swift 5, but my guess is that it's actually going to be later, maybe Swift 6. That's because there is some other work that has to get done in Swift that is going to affect any kind of concurrency model that would be built. And in particular, there's this concept of ownership that is going to be added to Swift that's going to change a lot about the memory model of the language itself. And if you're mucking with the memory model, that's definitely going to impact any kind of implementation of a native concurrency model. So ownership is basically the idea, it's basically who has the responsibility of destroying a value, cleaning up the memory for a value. In a language like C, for example, the ownership convention is that it's you, the programmer. You have to clean up that memory. In Swift we have arc, and that works well most of the time, but there is a performance penalty with automatic reference counting, and there are times when you might want to opt out of that, and right now that's very difficult to do in Swift. You have to drop all the way down to the level of unsafe mutable pointers, which is no fun. So ownership is about adding these annotations to the language where we'll be able to tell the type system something about whose responsibility it is to clean up memory. And then the compiler is going to be able to statically analyze what we're doing and do that very efficiently. So that's like a really high-level, probably incorrect explanation of ownership. But if you check out this ownership manifesto on the Swift repository, it's in the docs directory on GitHub, they talk a lot about what they have in mind. And the first step is actually a proposal that's already been released, and I think accepted, which is SE0176. That's about enforcing exclusive access to memory. And both of those documents, by the way, have sections specifically on how this would affect any kind of concurrency model. So a lot of them went over my head, I'll be honest with you, but you can actually follow along with a lot of it as well and get a lot out of it. So although we don't know a ton about what a native model is going to look like or exactly when we're going to get it, we can look at some native models that exist in other languages and imagine what those might look like in Swift. So there's 3 of those that I want to touch on: green threads, promises, and the actor model. All right, so green threads. Green threads are basically a user space reimplementation of the same threading interface that is provided by the OS. So you can create threads, you have locks and mutexes, you can start and stop threads. And you might be wondering, why would you want to re-implement that in user space? Well, there are a few benefits to it. First of all, it's safer. But second of all, when you have this re-implementation in user space with a user space scheduler, it can be a lot faster and a lot more lightweight. So unlike an operating system thread, which is very heavy, which has a lot of overhead associated with it, a green thread is very lightweight, very cheap to create and to destroy. And so once you have these, it can be easy to design systems where you spin up thousands or hundreds of thousands or maybe millions of threads and set them off to do work. So I could definitely see green threads, which exist in languages like Go, for example, coming to Swift as a kind of primitive in the language, maybe a first step. Another model that we see in other languages is the promises model. And we see this in JavaScript. It exists elsewhere. But promises basically are placeholder objects, and these objects stand in for the future return value of some kind of asynchronous function. So somewhere where you would otherwise have a callback, you instead work with this placeholder promise object, and then you register handlers to process those results. You can chain operations together, and you can do nice things like catching and handling errors all in one place. So it kind of linearizes code that would otherwise be callback based and makes it a little bit easier to deal with. There are actually libraries in Swift right now that implement some of the functionality of promises in Swift. So they're using GCD and I presume OperationQueues under the hood. Actually, our keynote speaker, Sarush, has a popular promise library called Promise. This is a code snippet taken from the README documentation of that library. So here we have this fetch users function, and this would be presumably hitting an API somewhere. And where we would normally have a block-based callback or a closure-based callback, we instead get back this promise object that has a generic type with a list of users. And then once we have this object, we can chain operations to it with the then keyword, and we can catch errors all in one place. So you see how it makes working with what would otherwise be nested callbacks a little bit more straightforward. All right, so let's move on to one more potential concurrency model that I want to talk about, the actor model. Okay, this is the wrong actor model. Let's talk about the programming actor model. And tough crowd, that fell flat. All right, so in programming, the actor model are entities, and these entities are standalone entities that can send and receive messages. So we're used to message passing if we've done work in Objective-C. But actors have a lot of other properties that are different from Objective-C objects. So actors maintain private internal state. They maintain state, but that state can never be touched by the outside world. They also have a built-in queue or a mailbox, so when you send a message to an actor, it actually goes into this mailbox. Multiple other processes might be sending it messages. They'll all just queue up, and the actor will handle them one at a time. So each actor runs inside its own single lightweight process, so you can think of this as running inside of its own green thread, for example, and it will never execute outside of that process. So the actor is basically the fundamental unit of concurrency in a system where you're using the actor model. And this is very different from the kind of code that we're used to writing, but I've had the opportunity to learn a little bit about it, learning Elixir over the past year. Elixir is a language built on top of Erlang. Erlang was one of the earliest languages to implement the actor model. And so when you build systems in a language like Elixir or Erlang, they end up looking something like this, where you have all these different actors. They all kind of stand alone. They have a mailbox, their internal state, and you're just passing messages in between them. And they take actions based on those messages. But usually you're not just going to have 3 actors. You're going to have maybe thousands or, again, even millions of actors. And because actors are so isolated, if one of them crashes, it can't ever impact another part of the application. It can't take down another process, another actor. And so actor model systems are very, very fault tolerant. If one of them goes down, you just restart it. You provide it with some default state, or maybe load the state from somewhere else. And these systems, again, it's a different way of thinking, but essentially what the actor model does is it takes away all the kinds of mistakes that you can normally make with concurrent programming. So we talked earlier about how anytime you have shared mutable state, you have to be very careful about how you access that shared mutable state. Well, in the actor model, you have mutable state, but it's not shared. So right off the bat, that idea is gone. There's a lot of other properties of the actor model that are nice, but I can imagine this coming to Swift, but I have maybe a little bit of a harder time. So if you were to imagine it, you could say maybe there's an actor protocol, and you have to implement a function where you receive messages, and then you pattern match on those messages and extract a payload and then take some action. And an actor would have to have a process ID and a mailbox, and it would have to have the ability to send messages to other actors via their process ID. So we can imagine something like this. I hope we do get it someday, but it's actually hard. It's not something that we can implement ourselves. There's no real good libraries implementing the actor pattern in Swift, and that's because the restrictions that you need to place on actors, we don't have the ability to express that in the language as third-party developers. So the actor protocol, for example, would have to enforce that an actor didn't have any shared mutable state. There's no way to express that in the language itself. So we need some help in the core language if we wanted to implement something like this. Now there actually is a precedent for that, the codable protocol that's being introduced in Swift 4. That's something that you couldn't implement as a third-party developer, but it gets special treatment in the compiler. So perhaps we could see something like this put into Swift in the future. So at this stage, I just want to really briefly give you some of my own predictions and opinions. Nobody's really asking me for them, but I'll say that we're all part of the Swift community, right? It is open source, it's developed out in the open, and anyone can get on the Swift evolution mailing list and contribute to the discussion. And so I do think we should all feel comfortable voicing kind of our opinions about the direction that we'd like to see this language that we all use go. So first of all, I think it's a pretty safe bet that we're going to see over the next year or so progress on this ownership system in Swift. And the memory model is going to start to stabilize. And I think as those things get completed and start to land in Swift, I think that we'll see the beginnings of a very vigorous debate on the Swift evolution mailing list about what a native concurrency model might actually look like. And I think that that's, and I mean that in a healthy way, like a healthy, good debate, because it needs to be debated, it needs to be discussed. After that, and this is where we stray into just predictions, or opinions, not really predictions, I'd kind of like to see some sort of concurrency primitive added to the language, maybe like green threads. And once we had those primitives, the community itself could experiment building libraries around different patterns and see what felt Swifty, see what felt best in Swift and felt native. And at that point, possibly the core team could consider expanding the standard library or building into the language itself some more opinionated, higher level concurrency models like promises, for example. Maybe we could also see, at some point, the language itself expand to give us something like macros, so that as third-party developers, we would be able to implement some of these more advanced pieces of functionality, like the actor model, for example. So, that's really all I have. The code that I showed, along with a section of resources, if you want to do further reading on any of the things that I showed today, is available up on GitHub. I guess we might have a little time for questions, or if there are any, or feel free again to reach out to me and talk to me during the rest of the conference. Any questions? Jaime?
Of the different types that you mentioned here, or concurrency improvements, where does C-sharp's async await fall into classifications?
Yeah, really good question. So the question was, where does async await, which you may have heard of in C#, I think it also exists in JavaScript in the form of different libraries, where does that fall into these models? So async await you can kind of think of as basically an extension to promises. So usually they're paired and used with promises. It lets you write code that kind of looks like the normal linear single-threaded code that we're used to writing, but you're basically annotating your functions and your calls to those functions with things like async and like await. And what await will do is tell the given line of code will block until that asynchronous call actually returns. So you write the code that looks linear, but it's actually running asynchronously and blocking until those things come back. And again, it's kind of like an extension to promises, and I could also definitely see that being something that is brought to Swift. And there are actually some libraries in Swift that implement it today. I think there's one called Hydra that has promises and also async await on top of it. Thanks for the question. Yeah?
Yeah, can you elaborate on what the difference is and why a green thread is much more lightweight than a regular OS thread? Because it was my thought that an OS thread is much more lightweight than the setting up a new process itself. So at least a green thread is much more lightweight than like a regular OS thread.
Yeah, that's a really good question. So the question is, why would a green thread be more lightweight than a regular old operating system thread? So I have to admit, I'm a little bit out of my league here, but here's the understanding that I have of the situation, right? So an operating system thread has to include and build up a whole bunch of protections for like the memory that is being freed up for it, and you know, to make sure that it only runs within the current program that it's being given, right? So there's a whole bunch of low-level kind of system call stuff. The operating system has to make assumptions and protections when it creates that thread. Whereas when you're talking in user space, well, everything in user space is already protected by the operating system, right? So a user space thread can kind of just be a very lightweight, simple thing that's created in memory. And then the other thing that you get is you have usually you have a user space scheduler. So you're not relying again on the operating system scheduler, which has to make a whole bunch of assumptions and protections. You have something in user space that decides when these threads run, and that user space scheduler can, again, be tuned and be optimized in ways that you can't when you're writing at the operating system level, and you can't make certain assumptions that you can in user space. So that's my best explanation. Might not be completely accurate, but that's my understanding. Good question. Sure.
If you were to use the promise technical, would you have been able to optimize that code as well as far as having shared access to the arrays and things like that?
Yeah, that's a great question. So basically, the question is in the promise model, how do you protect access to shared memory, shared mutable state? So I'll admit here, I have not had a lot of experience with using promises. A lot of languages that use it, like for example in JavaScript, I mean JavaScript itself is really a single-threaded language. So it's not even, you don't even have things running concurrently at the same time. So maybe in JavaScript they don't even have to think about it. It's more about taking things that would be callbacks, that would be asynchronous, and making it cleaner and easier to reason about. So in terms of your question, I guess I'll just have to say I'm not really sure. You might end up having to do similar things, or maybe there's some extension like in C# where it is possible to have real parallelism that protects against that. I'm not sure. Good question. Yeah, so the question is there any kind of performance penalty associated with jumping from GCD to an OperationQueue? So OperationQueues themselves use GCD under the hood. That's an implementation detail. You don't really have to worry about it, but you're using all the same kind of primitives that GCD provides. You're just using an interface that's a lot nicer, that's object-oriented, that provides you some additional features that would be hard to code in GCD yourself if you had to do it. So there's definitely some overhead in terms of the fact that you're dealing with objects, and they're Objective-C objects, so there's Objective-C message send now instead of a C API. My guess is that for the kind of work you would be reaching for an OperationQueue for, those differences are going to be completely negligible compared to the actual things that you're trying to parallelize in the first place. So in my opinion, if an OperationQueue fits better and allows you to produce nicer code, it's probably the right choice, and you wouldn't need to worry about any kind of overhead. All right, well, thank you for your attention.